Thank you very much, Tommaso, for the introduction, and also thank you for the opportunity that I can give this talk today in this colloquium series of ESMTB. So in the talk, I will summarize our works over the years related to waning and boosting of immunity. But before getting to that, I'd like to make some short announcement advertising our schools. So if you have any students interested, we will organize 2 summer schools this summer. One will be in cancer modeling in June, and we have Tommaso as one of our lecturers in the school. And we have another one in mathematical epidemiology at the end of summer in August 26 to 30. One thing which is important to mention that there are no registration fees to these schools, and even the local costs we can cover for students. So it is very good for opportunity for students who are low on funding to attend our schools. So over the summer, there will be other mathematical epidemiology schools across Europe. So there will be one in Belgium and also in Sweden. So if you have students, you can send around this summer, and they can learn a lot about mathematical epidemiology this summer. So the reason we can do these schools without registration fee and even covering local costs is it comes from the budget of these 2 institutions in Hungary. I'd like to just mention one sentence about these initiatives. In mathematical biology part in Hungary. So we have the National Laboratory for Health Security, which was evolved from the National COVID Modeling Task Force that we have during the emergency period of the pandemic. And now it's a large network of researchers covering large number of disciplines from mathematics, epidemiology, ecology, medicine, data science, biostatistics, and so on. So I work in 4 divisions, overall 250 researchers now in our national laboratory, and roughly 30 of them are mathematicians. So mathematics is a little bit of the organizing principle around all these many areas, which we generate large amount of data from different sources. And we also have, it is more on the medical side, the Hungarian Center of Excellence for Molecular Medicine. It was built up from a large European grant, and it is focusing on translational medicine and healthy aging, but they also have core facilities which are serving all the research groups. And one is scientific computing core facility. One we had a supercomputer just started to work 2 weeks ago. So there is also some mathematical modeling there in the computational medicine group within this institute. And the cancer modeling school will be from the budget of HSEM, and the mathematical epidemiology school will be organized from budget of the national laboratory. So these organizations support these schools. Okay, so let's go to the essence of the talk today. So many epidemiological models, compartmental models that are in use assume lifelong immunity after recovery. But of course, we know it's very often not the case. So the simplest framework to include waning of immunity is the SIRS model, when we have this just 3 groups, 3 compartments of individuals constituting the population, the susceptible, the infected, and the recovered. And after a while, when the immunity of the recovered individuals is waning, they can move back to the susceptible compartment, and potentially they can be reinfected. So, of course, we can make finer models rather than these 3 compartments. And if you look in the literature, you see this SIRS, SCIRS, or sometimes they use these indices when you take many compartments in a chain. So, for example, individuals going through different stages of infection go to I1, I2, I3, and so on. Sometimes these chains are introduced just to reflect different type of distributions of sojourn times in compartments. But if you make these longer chains, it has been observed a while ago, for example, in this paper in 1981,
that this gives us the possibility for limit cycles, which we don't have in SIRS model or SIRS in the ODE, basic ODE settings. But if you take more compartments or longer chains, then you can have oscillations. Like a Heathcote and Coaters, they observed that if you take 3 R compartments in the SCRS model, then you can have off-bifurcation oscillations. So we looked at this in a systematic way with my student Tamás Tekeli. We called it just multi-stage SIS, but in fact, it covers all SEIRS models as well. If you just think about like that, we have the last infected compartment. If its transmission rate is 0 or the first one, they can be think of these are the E compartment, or the last one is the R compartment. So it covers also this S and many E, many I, many R compartments in a chain. So the main conclusion from this work was that endemic equilibrium, whenever it exists, is always stable if this chain is at most length 3. But if you have 4 or more compartments in the chain, then there exist parameter sets that the endemic equilibrium is unstable. And also there exist parameter sets when it's stable. So it also already gives an interesting question when in reality, we have continuous transitions and we discretize it into separate compartments. But if you discretize it into 3 or not more than 3, then you will lose oscillation. So that's an important thing to keep in mind for modeling, that depending on how you discretize, you can have different dynamics. So, and of course, in applications, we want more involved epidemiological models that includes many heterogeneities within these subpopulations. Susceptibles can have different behavior, for example, depending on socioeconomic status, or different contact patterns depending on age. Infected individuals can also have mild, moderate, or severe infections. And also the recovered ones, their immunity also shows great heterogeneity. So in this talk, we would like to focus on this part and include the heterogeneity in level of immunity in these compartments. So what I will use as an analog is an immunity conveyor belt to build our model. So you can imagine a conveyor belt which is moving in this direction. And this will consist of the immune individuals. So we put them on top of the conveyor belt. Like upon recovery, somebody starts here with high immunity. As time goes on, they move along the conveyor belt as their immunity is waning. And after a longer period of time, they can just fall off at the end and become susceptible again. So this is a simple concept of waning of immunity. And now we go to boosting. So boosting is also very important for many diseases. Boosting simply means if you re-exposed to the pathogen, if you have some weakened immunity, but you re-exposed, then you can boost your immunity and it gets stronger again. Similar concept holds for boosting doses of vaccinations, booster doses. So again, we have an individual here going down the conveyor belt, but before falling off, it may get a boost and then jumps back to a higher position on the conveyor belt, and then going down again. So this is basically this very simple idea of waning and boosting. And now we try to formalize this. So you can imagine that the level of immunity of a person going up after a primary infection, over time it starts to decay, but then with new exposure, it goes up again and decays again. So then we have, of course, many individuals who were infected at different times. So we are dealing with density of immunities. So I just, on this simplified conveyor belt, I just want to emphasize here, we have densities of individuals, basically, what we're dealing with. So now we look at the SIR model. It's not the usual order. So from S, I mean, in the visual display, from S, we jump to the I compartment. And after recovery, we start with here, Z max will be a very strong immunity and waning while in the R compartment. And when we reach Z min, we jump back to S, but we have the possibility of boosting and jumping backwards. So we want to formulate this.
mathematically, but before doing that, there is a warning. So what we do here is just we express the level of immunity with a scalar quantity now, while in reality, immune system is incredibly complex. So basically we take, even the model will be much more complex than just SIR or SIRS, simple compartments. It's still just a one-dimensional projection of an incredibly complex immune system. So with Maria Barbarossa, we wrote down this general formalism in a PDE form. So this is a kind of SIR model. Then susceptibles are, as usual, individuals are born into the susceptible compartment. They get infected, they can die. And this is the inflow from those who are just losing their immunity and becoming susceptible again. They appear in susceptible compartment with the plus term. I will specify this a little bit more in a second. And individuals, of course, they arise with the incidence term, so the new infections, and they can recover, die naturally, or die because of the disease. And now we structure the R compartment with respect to Z, which is the level of immunity. So here we have a waning rate at which speed the individuals losing their immunity, so moving along the conveyor belt. Of course, in the process, they can die. And now this is the boosting term with respect to getting in contact with infected individuals. So this is re-exposure. So and we also have a kernel function P, which should be very important, which basically tells us that if somebody is at a given level of immunity, to which level they will jump, or how they are, those who are boosted from a given level, how they are distributed at higher levels. And this minus R is simply those who are boosted out from the actual level of immunity. And then those who recover from the disease or who got the maximal boost, they will arrive here at the boundary condition at maximal immunity. So that's a PD formalism of this conveyor belt with waning and boosting. So in this general setting with the PD, we can do some analysis. We showed well-posedness and disease extinction and reproduction numbers smaller than 1. But if you discretize the PD, you can recover a variety of OD systems. So here is just one example. When I discretize the immunity, structured immunity into three levels, and after recovery, you come up with a strong immunity, then it gets weaker, and then it's even weaker, and it goes back to susceptible. And meanwhile, by re-exposure, you can get boosted back to some of the higher levels. So now we can see even for this simple OD, you can have different boosting mechanisms. For example, from RC, what do you assume? You go back to the larger one, or just jump one level up? And these are different mechanisms. So we looked at the PD from numerical point of view and compared different boosting mechanisms. So that one simple case, when there is no boosting, then an individual just losing their immunity and then becomes susceptible. There is one possible mechanism that basically resets your immunity whenever upon a re-exposure, immunity is boosted back to the maximal level, or boosted a little bit somewhere in between. So of course, this can be depending on the actual Z. And there were two very different approaches in the literature when from in-host models, they were estimating this updated immune level from the immune level before the exposure. One is Heffernan and Keeling, other is Odo Dickman and Couters. So from in-host models, they generated these functions, completely different models, but the outcome is very similar, as you can see. So here is initial immune level, this axis, other axis is updated immune level. So we compared now different boosting mechanisms for the PD. Sometimes PD has a stable equilibrium, like in this case, you can see for different boosting mechanisms, you have different prevalence at the equilibrium. One thing you can now look at is the stationary distribution at the endemic equilibrium. So what is distribution of immunities? And now we can see that for different mechanisms of boosting, you can have very different distributions.
And even for those ones which are derived from in-host models, we have this kind of little cusps here because of the flat part here at the bottom. So these are stationary distributions, which are very different for different boosting mechanisms. But the waning boosting PD can also be oscillatory. So if we plot solutions with different parameters, this is time and immunity level and the distribution of individuals. So R is on the other axis. We can see these periodic patterns, or sometimes even more complicated looking than periodic. So I have some videos to play these. So what we see in the video no stopped. I restart them. So what we see here in the black in the bottom left. So this is the no boosting scenario, and basically we see kind of traveling wave behavior. We have repeated outbreaks, and after every outbreak, it's very intuitively very easy to understand. After a large outbreak, you have lots of immunity, high immunity individuals appearing here at the left end. And time goes on. They move all together, losing their immunity, and at the end become susceptible. So if we had a very large number of infections in a relatively short period of time, then they will lose their immunity roughly at the same time. So then suddenly new susceptibles will appear, and there'll be a new outbreak, and that repeats. So that generates this behavior. So if we have additionally we have boosting, then you can see the shape is very different. It's not a traveling wave type anymore because the boosting always pressing the immunity upwards, and we can compare it with the Diekman and the Heffernan types boostings. I can find this. Maybe I go back just one sec if I can. I can find this little cusp at the bottom. Maybe you can see it's a specialty for this boosting mechanism. Okay. So if we consider even the simplest OD version, so that just has 4 compartments: susceptible, infected. Well, R and W is for waning compartment. So these are still immune, but they can go back to susceptibles. So even this one, the simplest OD, and I highlight this other term here for boosting. So basically, it means that if individual with waning immunity gets in contact with an infected individual, can jump back to the higher immunity level compartment. So beta was transmission rate, and we have an additional parameter here, nu, is sometimes we call it boosting force or boosting level. So how basically it reflects how more often or more or less frequently we got a boost compared to an susceptible getting an infection by the same exposure. So we have now two nonlinear terms from S to I and W back to R. So this model was used to explain pertussis dynamics, the different cycles that were observed in pertussis in these papers, Lavin and co-authors. But it was an age-structured model there, so there were different discrete age groups, and you had this SIRWS structure within each age groups, and they even fitted it to the data and estimated the boosting parameter. And then for the OD, for the 4-dimensional, so not age structure, homogeneous population case, this team from Australia, they were looking at the bifurcation diagram, and they already found interesting bifurcations for this model, and a different approach using singular perturbation theory by these authors. They mathematically proved the existence of limit cycles in SIRWS models, which are not present in SIR or SIRS. So they really crucial that this boosting that is there that generates these behaviors. So we made a follow-up study of this SIRWS model,
from bifurcation analysis point of view. And the key difference what we added to these models is that in all the previous models, if I go back to the model, they use the same rate from R to W and from W to S. From R to W and W to S, just for simplicity. So we looked at what happens if we allow basically different duration times for these parts of the immunity. So R is when you have strong immunity, V is when you have somewhat weaker, but that can be boosted back to R. So how the relative lengths can change the dynamics. That's what we were looking at. And it turned out, this is just explained here. So the previous papers were all this special case. Here alpha omega R equals 2, so then equally distributed times. So now we looked at unequally distributed times between the boosting and the non-boosting periods. And it turned out we can have bifurcations with respect to this partition of immunity parameter also. So if you change this partition, you can change the dynamics, basically. So in this chart, what we see is stability region of the endemic equilibrium, which is in red, and instability is in blue. And basically what it shows, even if you start to increase, basically we look at the boosting level as bifurcation parameter, start to increase it, then you have a stability switch from here. From stable, it becomes unstable until you in the blue, go up, becomes stable again. And you have the same if you go according to the other axis by alpha, you can have stability switches. Means that for some, if you are in between or within this region, you have oscillations and limit cycles. So, but it is even a little more complicated at this part. So I just enlarged the interesting parts. So here, this boundary of this stability region is not monotone. You have these little waves, and also down in this region, you also have some non-monotone. So if it's non-monotone here, for example, with this particular boosting rate, if you can have more than one stability switches. If you go horizontally here, you can cross the stability boundary several times. And also here, the B, capital B, means the bistable region. So it means it belongs still to the red domain. So the endemic equilibrium is stable, but there is also a coexisting stable limit cycle. And we can see this from the bifurcation diagrams plotted this way. So this is the basically prevalence at the endemic steady state plotted against this partition of immunity. So when alpha equals 2, that was the previous paper's special case. So you can see here two stability switches. We have Hopf bifurcation here. So this bubble shape, it shows maximum and minimum of a limit cycle for a given parameter value. So that's how you can, this is the endemic steady state, the dotted part when it's unstable, and this is emergence of a limit cycle by Hopf bifurcation there. Then it stabilizes back, becomes unstable again. And that was the lower part of the stability region. At the upper part, we have the even more complicated situation. Here also these red-blue curves, they representing the limit cycles, and red one is stable and blue one is unstable. So we can have really complicated bifurcations here, even in a simple ODE case. So there's another variation of this model when so far we just bypassed a biological process that when you re-expose to the pathogen, you immediately jump from W back to R. So this model takes into account a kind of mild infection that can happen when you re-exposed, and individuals go through a J compartment, not directly back to R, and it is J. While in J, they can also be infectious, can infect susceptibles. So this was studied by Lauren Childs and co-authors, but again, with the same waning rates from R to W and W to S. So we looked at again what's the effect if we allow disproportionate or different proportions of the two immune periods. And again, we have this complicated bifurcations. We also discovered that the backward bifurcation is also possible for this system. Backward bifurcation means that when the basic reproduction number is passing 1, typically we have emergence of endemic equilibrium, which is stable and exists for R0 larger than 1. But for some models, including this one, the transcritical bifurcation goes backwards first, and this is an unstable branch of subthreshold equilibria, and we have here the stable branch, which means in this interval, in this figure 0.9.1, we have 2 stable steady states. So this is free, locally stable, but an endemic also. This is because it's intuitively understandable that the J compartment can sustain the infection if there are sufficiently many individuals in the infected individuals in the initial value. J can sustain the infection even if reproduction number is slightly less than 1. So, and there are age-structured versions of this model that we developed. I just show very little about this. So this was still before the pandemic. We developed this model, and the notation is here slightly different. We have different levels of immunity, but we denote it by S. All these compartments, basically S1 is the fully susceptible. After infection and recovery, they can go to S5, which is the strongly immune here, and then waning, they can fall back to lower levels, but they can also have milder infection in between. Vaccination brings them not to the maximal, but one lower level. A booster vaccine can bring them back to the maximal. So we looked at this model from a point of view of vaccination strategies to look at how the outcomes are different when you have, it was also age structured with 29 age groups. So we could look at timing of primary and booster vaccines, at what age we give. So overall it was 261 ODs in this model, and then parameterized to pertussis in Sweden also, when there was a gap in vaccination for pertussis for 17 years, and we could confirm that after they restarted and determine the time for boosters. It was well determined. Yeah, and then the COVID came, and we also modified a little bit and parameterized to COVID as well, when we added vaccination also with the 2 doses now, because of that, of the COVID situation was like that. And what we could do from this model is that before vaccinations actually started, kind of looking at different vaccination scenarios and what kind of fall waves we can expect under different vaccination assumptions. But one other advantage of this model is just we can make seroprevalence estimates distributed among age groups, and also level of immunity, and also the number of infections we can stratify by severity with this detailed model. So in the last part, I'd like to talk a little bit more about one special version of the waning boosting model. I call it now max boost model. So basically this is the assumption when boosting is restored. Boosting restores immunity to the maximal level. So this assumption was already used in a very different context and different type of model in the 80s for malaria. But now we look at this model with this assumption: boosting fully restores immunity. And we also assume that in the absence of boosting, immunity lasts exactly 2 years. And we make the little simplification, ignore disease-induced death, normalize population to 1. So in this case, when boosting goes back to the maximum level, always, then all the boosted individuals will go to the boundary value and not in between Z-min and Z-max. So then we can solve the PDL on characteristic curves in this case, and express the other end of how many individuals are falling off at the other end of the boundary. So that we can express by the history, what was the state or number of infected and recovered individuals tau time before. And that leads to delay differential equation model. So it's not a PD anymore, but it has a time delay tau and also integral in the exponent here. So actually, this model we can understand even without going through the integrating along characteristics. So if we just think about how many individuals will lose their immunity at a given time. So who will these people be? So there are those who recovered tau time ago, which is gamma I is recovery rate. So gamma I t minus tau are those who recovered tau time ago. And in this time interval from tau minus t up to t, so in the last period of length tau, they have not been boosted and not died. Okay, so this in the exponent that reflects that they have not died and not boosted. This is the boosting rate integrated. So these are one type of people. Recover from the disease, never get boosted until go back to susceptible. But of course, some individual will be boosted. So, but because boosting restores immunity to maximum, those who are losing their immunity at a given time are exactly those who were boosted tau time ago, the last time. So that one again you can express. So this is individuals being boosted at t minus tau time. And since the last boost, they have not died and not received another boost. So adding these two together, we obtain the equations. So since it has time delays, it needs now different tool sets from mathematics, because the phase space of this system is typically for delay differential equations, a space of continuous functions, usually with supremum norm. So simply because to continue a solution, we need to know the history. If you just set up the initial value at t equals 0, you cannot understand the right-hand side because you have values from tau time before. So typically, in the function space we work on is a space of continuous functions, so some initial function. Then you start a solution, and you're always looking at the window of length of the delay and shift it back to the initial interval. And that's how you define a semi-flow in space of continuous functions. So if solutions evolve from this function here, we go to this function at time t. This is just a technical thing. There is another technicality with this model is that we cannot use the full space C because then solutions can go negative. So we need to restrict to this positively invariant set, which if we think about a little bit, we can show that this is exactly the biologically feasible initial history functions contained in this set. So for biologically relevant initial data, we have invariance of this set, so solutions remain feasible. So the analysis we did for this model, some were analytic. We had the usual threshold theorem. If R0 smaller than 1, this is extinct. If R0 larger than 1, this persists. Now we needed a persistence theory for semiflows because we work with semiflow in space C now. We had existence and uniqueness of endemic steady state, which is now not so easy because if I go back, if you set the right-hand side equals 0, you have the state variables here in the exponent also. So you have quadratic terms in the steady state equation, but also multiplied by exponent, which means that you cannot explicitly calculate the endemic equilibrium, but still you can prove an existence uniqueness. And then stability analysis becomes very hard. We discussed this in this paper with Maria Barbarossa and Monica Polner. And if you just linearize around the steady state, the max boost model, this is the characteristic equation you arrive to. So in one hand, it's not just polynomial because we have this exponential in the lambda e to the minus lambda tau terms there. And also, it's a transcendental equation with infinitely many complex roots. And also not even explicit because it includes I star, S star, which we don't have explicitly. So that makes analysis of the characteristic equation, hence stability analysis, difficult. So we can do a few things. Proved that the instability region is bounded, for example. So if you look at the spectrum, so the roots of characteristic equation, in one example, it looks like this. And if you change some parameters, you have these pairs, they can move left, they can move right, and they can cross the imaginary axis, causing Hopf bifurcations. And if you look at stability domains, then here the blue is stable, the pink is unstable. We can have these strange shapes. Or if we increase mortality, we can have even disconnected domains of instabilities. So recently with Francesca Scarabel and others, we were looking at numerical bifurcation analysis, a more detailed numerical bifurcation analysis of this model. And for that, we have a new tool, which we didn't have before when we first studied this equation. So this technique developed by the numerical analysis group in Udine is now built into MatCont. So basically, with MatCont, we can do the numerical analysis, numerical bifurcation analysis even for delay differential equations, which has not just a single constant delay, but also distributed delay because of the integral. So this tool can handle that. So this is a more detailed picture. This is the boosting parameter here and the time delay, length of immunity in the absence of boosting there. And you can see these are the Hopf curves, basically when you have crossing of eigenvalues. Of course, they intersect here and there. Then we have double Hopf point that's there. We also have these other points, the empty circles here. These are generalized Hopf points when the criticality of the bifurcation changes from subcritical to supercritical. So if you look at, for example, this part here, this is plotted here. However, we can see in this we have unstable, steady state, then it becomes stable, and again unstable again, and you can see this bubble-shaped bifurcation of the limit cycle, which is closing back when we cross this point again. Yeah, and then the MatCont can track also the period of the limit cycle in the meanwhile. And finally, I show two more bifurcation diagrams with slightly different parameterizations. So we could identify, Francesca could identify Nymark-Zucker bifurcation, so torus bifurcation along the branch of the limit cycle, also period doubling, and of course we have these turning points in the branches, which is here called limit point of cycles bifurcation. So what's interesting, I think it's important to mention. So there was before known for the simpler model, the OD model, bistability of a steady state and a limit cycle. But here we could also identify bistability of two different limit cycles. So two limit cycles, both stable, coexisting. And here they are in this figure. So one has a period 4.2 years, other one has a period less than 3 years. They have very different shape and length of period, and they both coexist. They coexist and both stable for some parameter configuration. So now, let me talk a little bit about consequences of this potentially complicated dynamics. So during COVID, there were very strict MPIs employed around the world depending on the country, for different periods and different stringency. And then basically brought down many other infectious diseases as well. So as a consequence, susceptibility in population increased in this period, both because of reduced exposure in the pandemic emergency period, and both because of demographic change. So in a few years, newborns came in, or in the schools have now new students who have not been exposed to diseases as previous cohorts. have been. So that led to resurgence of many infectious diseases once the MPIs were lifted. So in a simple modeling setting, you can imagine that we have here a stable state with MPI. In this period, we bring it down, and when MPI lifted, you have a large peak. Because in this MPI period, the immunity is going down. Or you can see the same. This is now seasonal version of the same model when you have seasonal outbreaks during MPI, immunity going down. After they lifted, you have a high peak. So, and then we can see it for many diseases. This is UK data for different diseases. Like here you can see this, for example, this is pertussis, but there's also many other diseases here. We had during pandemic period very low incidence, and after pandemic shoots up. What's interesting is that they are quite different. So some has a twice as high peak as it was before pandemic. For other diseases, it's 5 times higher or even more higher peak. So clearly many particular factors affecting these diseases like length of immunity, viral evolution, vaccination, and so on, they are influencing. Yes, so now if we look at, so this is again SIRWS model. So SIRWS model can have bistability. So the consequence of that, when we had this MPI period during the pandemic, potentially this intervention, this large perturbation could push the state of the system for any disease from one basin of attraction to another basin of attraction of another attractor. There's a possibility for that. So if that happens, it means that after MPI is lifted, the disease dynamics will not return to where it was before, but it will be something else. And numerically, if we can find simply examples, like this is one example here, when we have, so this is business as usual is the blue one. In the red one, we employed MPIs in this period. Then we had a large peak. And then after a couple of waves, it went back to normal. But there is also a possibility when it never goes back to normal. It will have settles on another stable limit cycle in the model at least. So the question is that can happen in real life or not. So here we have this is a naive fitting to pertussis because waning boosting is there in pertussis. So we will see what happens. So all these diseases now, post-pandemic, showing different dynamics than before and different from each other. So I think this is a very interesting period for disease modeling. And not just the pandemic was, of course, very intense period for disease modeling, but then everybody was focusing mostly on COVID. But this is also from modeling point of view, I think, a very exciting period, the post-pandemic years, because this MPIs was such a large perturbation that was basically unprecedented. So now to understand that which diseases go back to normal, I mean, pre-pandemic patterns, which are not, and why, and what happens with this disease, RSV, influenza, all other diseases can behave differently. So to understand this, we will see. But when there is waning and boosting, we know that complicated things can happen. Yes, so finally, I just thank my collaborators for these papers here. I listed them here. So yeah, we started to work with this on Maria Barbarossa and then Monica Polner, and later many others on numerical bifurcation analysis part, and then on the A-structured part with more application-oriented part. And now with this new advances in numerical bifurcation analysis for delayed differential equations, we returned to the MaxBoost model also recently. We can do much more than we could a couple of years ago. So these are the papers I've collected the content for the talk, and basically I just say one sentence summary. What I can say is that if we add immune dynamics into an epidemiological model, even in a very very simplified way, then the nonlinear phenomena will be really strongly present, and everything gets really complicated very quickly, even in the simplest models. So, and there are many questions, both mathematical side and both on the application side about these waning boosting models. A lot of work to do with them. So with this, I thank you for your attention.